Okay, so we left off last time with our pipeline analogy, and we noticed that we were going to get a 4x improvement in our processing speed. But we should first note that there are two ways to think about speed, and we've talked about them before. One of them is called latency, and one of them is called throughput. And we should note immediately here that the latency, to do one load of laundry here was 4 time units, 4 wash units or dry units or whatever. We're assuming they all take the same time. And down here, it's still the same amount of time to do, one load. It's just that they're overlapped. They're pipelined. And pipelining increases the throughput, but it doesn't change the latency. So that matters, of course, because there's no computer that is going to execute just one instruction. We're always going to be executing a gazillion instructions. And so improving our throughput, the number of instructions we get per unit time. So remember, throughput is number per time. And so improving that gives us, what we need if we want to design a faster processor. And so we said, okay, well, we're going to do better than that with our actual processor, because we're going to get a 5x improvement, because we're gonna divide the total length of time that we're going to use to do things into 5 stages rather than 4. And so we'll get a 5x improvement. And again, we'll note here improvement in throughput, but not latency. The amount of time it takes to do one instruction stays the same. So the stages, we're going to name them in a way that should make quite good sense based on all the discussion we've had so far. We're going to have the instruction fetch phase, which makes sense. First thing we're going to do is go get the instruction. And then we're going to read the register file. We saw how that happens already, that's the first thing we need to do is read the operands out of the register file. And we got a hint that at the same time, we're going to figure out, what it is we're doing. For example, our favorite signal, the branch signal, we're going to decode and see that, oh, this is a branch. And therefore, we're going to use this signal to control that AND gate that decides whether we continue on to the next instruction or whether we branch off somewhere. So we do that instruction decode. And then after we read the operands from the register file, we're going to do some ALU type, as we call it, instruction. And that means that, we're going to do an add or a subtract or something like that. And we call that here the execute cycle, the execute pipe stage. So we're going to execute the operation, whatever it is. And it's possible that the execution will not be an ALU type, but instead will be a load store type. And if it's a load store type, of course, we're not going to add 2 values to put them back in the register file. Instead, we're going to compute the address. Remember, we're going to do the base plus offset. We're computing the location in the data structure for we software people. So where in the data structure are we going to go? These fundamental things. We either do some arithmetic operation or we're going to compute some address. And then if we compute some address, then we're going to go here and in the memory cycle, we're going to actually go get the operand. And then we saw that if we do this, if we execute some operation, we're going to not do anything with the memory and we're going to go around it and go right to the writing of the register file. But we won't. It's a key point here. We never collapse out a pipe stage. The pipe stage will always be there. So we may not do anything during the pipe stage, which is what happens in this case when we go from execute to write back. We won't do anything here in the memory stage, but the memory stage will still be there. It's just that clock tick will go by and nothing will happen. And it'll become, very obvious why we do that when we look at the pipeline all stacked up. I mean, there's no real way you can compress it out because everything will get out of alignment if you do that. So anyway, so here's our 5 stages. You should, obviously commit these to memory, although you won't really have to memorize them. It'll be, you'll just naturally think of them as you look at the picture of the execution unit. What you do in each stage is pretty clear, pretty self-explanatory. So the names should be very simple to remember. So 5-stage pipeline, your standard high performance pipeline. So the way we get speed up, of course, is as we said, it's going to be via throughput. And we want to balance the stages. We want them all to be the same length, and we're going to work very hard to make that true. So we're just going to assume that that's true. And of course, one of the reasons it's true is we want the clock to run at a constant cycle time. We don't want the amount of time in a clock cycle to change. We want that to be very stable. And so we'll just take the total time that it took to do the whole thing that we've been looking at for the, in the last lecture, how long it takes to go from the beginning to the end. And then we divide that by the number of stages that we are going to divide it into. And we know this number is 5. And then the speed up then is due to increased throughput. So we'll get an instruction completed every cycle. Again, it does not change the latency. The total time for each instruction stays the same. But every clock tick, we're going to get a new instruction done because we have them all pipelined. And again, you say, well, how can you pipeline it? Well, you pipeline it the same way you did the laundry. You just have to make sure you're doing some distinct thing in each pipeline stage. As long as those things are separable, and we'll see how they're separable. As long as they're separable, you can then stack multiple instructions together. So the idea that you were going to pipeline the processor, that wasn't an afterthought. So they didn't say, okay, here's, the way we've come to it is we designed everything that had to be done. And then we said, okay, well, now we're going to pipeline it. And if you do that, then it may not actually pipeline very well. But in reality, the way this was done is that it was known that you want to build an architecture that can be pipelined, because it's known that that's how you can increase the throughput. So you design the instruction set architecture for that. And again, since MIPS and ARM and RISC-V are all the same, we can make the same assertion, about all of them. They're all designed to be pipelined, and they're all designed to be pipelined in the same way. And generally speaking, all the instructions are 32 bits. Turns out for all these architectures, all three of them, there's a half size instruction version where the instructions are 16 bits. And they do that specifically so that you can make certain types of applications. You can make the amount of code how much space the code takes up in memory is smaller. But we're going to completely ignore that and just assume that all instructions are 32 bits. We are going to completely, totally ignore that all three of these guys have a 16-bit format. So we want as few instruction formats as possible, and we know that we only have three. We have basically the ALU, the load store, and the branch, just those three types. So we want as few of those as possible, because every instruction type you have will have, its own control and its own, particular things that it has to do in the data path. So you want this to be absolute minimum. And then again, as the thing we learned in the very first lecture, and that, that you guys have done quite well understanding and adopting, is that you can only access memory one way, and all you get is a constant plus a register. That's the only way you can do it. You have that constant, and you can add it to a register. So it's the register represents the base address of the data structure, and the constant is just how far into the data structure you're indexing. You're indexing into that data structure, and that's all you can do. It's the only addressing mode that we have going out to memory, and that just keeps the design as simple and as fast as possible. And if you want to do something different, the compiler has to do multiple instructions to do whatever it is you want. And again, here, the modern versions of these three architectures don't require alignment of the memory operands. Having alignment is really, really good in the design. It makes the design much simpler. But sadly, because there's so many data structures out there that are generated by the Intel architecture, the x86, which does not require alignment. There's so much data out there that's misaligned that all of these architectures have had to allow unaligned. And they may not do it. They may do it in a very simple way that doesn't give great performance, but they do allow it. They permit unaligned references. Now, for us, in the simulator that we're using, everything has to be aligned. If you do anything unaligned, it will give you an exception, which is how it should be for learning the material. All right, next, we're going to need to learn a whole bunch of new magic tricks. Because once we pipeline the processor, we're going to see that we're going to need to make sure that to use an analogy, that when we go from the dryer the folding table, that we make sure that all the socks are there, that you know, that you didn't lose. If you left a sock back in the washer, you know, stuck somewhere inside the washer, and it didn't make it through the dryer, and therefore it's not ready for its pair in the folding table, we're going to basically learn, you know, all the magic tricks necessary to solve the missing sock problem here. Solve the missing sock problem. And so we're going to talk about, you know, 3 different types of hazards, and we'll come back in just a couple minutes. We'll just take a short break here, and come back and start working on this. Okay, so we have our 3 types of hazards here, and we'll call them again all the 3 different missing sock problems that we have to solve, and we have them, you know, named here: structural, data, and control. So 1, 2, and 3. These are our 3 types of missing sock problems. And the first one we'll solve easily. We'll just add resources. So it says a required resource is busy. So to solve that problem, if there's some need for a resource by 2 different stages of the pipeline, we'll just add resources to make sure that doesn't happen. The next 2 and 3, the data hazard and control hazard, those won't be nearly so easy to solve. And over the next few slides, we'll look and see how to do that. But both of them basically are the problem is that you're waiting on something to happen. So notice that this appears in both of them. So some previous instruction did something. And again, you'll recall the latency of our instructions didn't change. So when that previous instruction does something, if the thing that you need isn't available till the end of that latency period, and you started another instruction, and the thing that you need isn't to the end of that instruction yet, you're going to have to solve that problem somehow. And so that's what we're going to do, and that's that's where the magic trick portion comes into this, that we're going to have to use some simple and some very, very powerful magic tricks to get around this waiting for something to happen, because we don't want to wait. Anytime we have to wait, the pipeline stalls and we lose our throughput. Our throughput goes down as soon as we have to wait for anything. All right, again, so in this pipeline with a single memory, if we only have a single memory, if we think of our processor as going to external memory, then we have a problem, because when we overlap the stages, there's 2 times that we go to memory in the load store instructions, because we go to memory to get the instruction, and we go to memory to do the load or the store. So because of that, we can't overlap those things, because we have 2 things that are, once we stack the instructions together, we're going to have one of them trying to access the memory to get its instruction, and we're going to have one of them trying to access the memory to do its load or store. And so that doesn't work. And therefore, what we're going to do is have separate instruction and data memories. And that shouldn't be a surprise, because the picture that we've looked at for the last couple of lectures doesn't change. We already drew the picture with a program counter feeding an instruction memory. And then later on, we had what we called the data memory. We already had in our mind that those two separate memories existed, even though conceptually we were always saying we were going to go to main memory for those things. We drew them as two different blocks. And in fact, on the processor, we're not only going to draw them as two different blocks, they are two completely separate pieces of memory. And in fact, we talked about the finite state machine. Remember the finite state machine that goes to either the instruction cache or the data cache. And we showed how it goes to one or the other, or it goes to them in a specific order. We looked at that finite state machine. So for right now, we can just think of it as having two separate memories. And in chapter 5, we'll see that those memories have this have this very specific, cache organization. And we'll learn why that cache organization exists and how it works and how many levels of it there are. We'll learn all of that in chapter 5. For now, we can just say, okay, we got two memories, and so we will, get rid of this structural hazard. We'll just get rid of it by having these two memories. Now, the data hazard, this will be our one that we spend the most time on, because it's the most common, and it'll give us the foundation for how we also will address the control hazards as well. So the data hazard is illustrated by this piece of code here. And we want to talk about this piece of code for a second, because we're going to solve the problem that this piece of code illustrates. And we ought to have in our mind, of course, before we solve a problem, whether the problem is important, whether it's worth solving or not. And so we look at this piece of code, we can ask ourselves, well, how often does it happen that you compute some result, and then you try to use that result in the very next instruction? How often will that likely happen? And of course, the answer is it's going to happen almost every time. I mean, that's the nature of a program. I mean, the reason you calculated this was because you needed it, and you needed it to do something else with it. And you're not going to wait to do that. I mean, you computed it here because you needed it here. So this will happen all the time. So it's really quite necessary that we solve this problem. And the problem is, illustrated here. Here's our pipeline: instruction fetch, instruction decode, execute, memory, and write back. Here's the 5 stages that we've conceptually divided our pipeline into. And the first question we ask ourselves is, okay, well, from the point of view of having the result, of actually having this result, the number itself, the essence of the result, which is the value, when do we have that? And well, we have it right here. We have it at the output of our ALU, of our adder. When we get to the output of that adder at this point in time, we have this result. And we're not going to write it back into the register file until the write back stage of the pipeline. And so if you look at it from the point of view of just simple-mindedness, if we have this second instruction here that needs it, well, we need it at the input of the adder. So we need it right here. And just, we'll talk about this, many times, but by convention, this guy is the top input of the adder, and this guy is the bottom input of the adder. So of these two columns here, this is the top and this is the bottom. So we need this result. We need it here. And so the way the picture is drawn here, we delay this instruction by 2 instruction. I mean, we'd like to have started it here, but we don't start it there. We don't start it here. Instead, we started here, and we started here because we can't read the register file. And that's the normal way we get this value, is we read it from the register file here. So we wrote it here. We wrote it in the first half of this cycle, and we read it in the second half of this cycle. So we wrote it here. We read it here. So wrote, read. And so it's ready to go. And so we can do this execute here. But you see that this just, killed our pipeline. It introduced, 2 instructions into it that are both no-ops. And so all that work we did to pipeline the processor just basically went away. And so we can't allow this to happen. So we need a magic trick. And so here's our magic trick, and we put the second instruction immediately after the first instruction. And even though we're going to take this value and not write it, we're still not going to write it into the register file until here. We know that we have it at this point in time. And so we're going to forward it or bypass it. These 2 words are used interchangeably out there in the design world. We're going to forward it or bypass it right into this input of the adder. And of course, you can immediately see from what we've said in the past that you're not going to be able to do this. You're not going to be able to just attach that wire to that wire. That just won't work. Both these things can't be driving that same point. Electrically, that doesn't work. So we know that what that means is we're going to have to put another mux in here. So in general, you will find that magic tricks, require muxes. So every time we need to do a new magic trick in our processor, we're gonna end up with more muxes, and we'll have gates too, logic gates. But the signature, the signature of a trick will be that a bunch of muxes will appear. And of course, this could also have to go to here if this instruction, if the S0 were here, so if these were reversed, then this guy would have to go here instead. And so that means you have, a mux there. And so the key point is, again, we'll use the result as soon as it's computed. We won't wait for it to be stored into a register. And this will require extra connections in the data path, as we've shown. And those connections will require these muxes. And again, we just want to recall that we must solve this problem, because this kind of thing where you compute a value and then immediately use the value is going to happen time after time after time. It'll just every sequence of instructions we've ever looked at and that you'll ever look at in the future will do this, because that's the nature of programs. Okay, so having gone through that one, we'll again just pause for a few minutes and give you a chance to think about it, and then we'll come and start, and we'll do the load to use data hazard, which is the next biggie. Okay, so for the so-called load to use, so load to use means that we've done a load instruction, and we want to use the result of the load instruction. And so we see that here in this sequence. We did a load into S0, and then we are going to use S0 in the very next instruction. And so again, you can ask yourself, well, how often does this case occur? And of course it occurs, again, constantly. The reason you did the load was because you needed the value in order to do something to it, which you're going to then do as soon as possible, very likely on the next instruction. So here to solve this problem, we'll note that, well, it's not even completely solvable. We've already shown the case here where we didn't wait. So we didn't wait for the reg file write. We're already showing the magic trick here, because when do we have this value? Well, we have it at the end of the memory cycle. That's when we have the value. We haven't written it into the register file yet. And then we need it into the input of the adder, again shown here. And so we draw that line directly, but notice that because we don't have it until here, in the previous case we had the result right here. But in this case, the value that we have here is just the address that goes to memory. We don't actually have the result of the load until the end of the memory cycle. So the earliest we can forward the result of the load is from this point here. And that means that this instruction is delayed by an instruction from the load. So the use of the load is delayed by one. So this is bad, but we can't do this. We can't move this guy here. I, F, I, D, EX. We can't put EX there, because to put EX there would require us to do this, right? And note that at this point here, we're already at 800 picoseconds in time, and this would be sending it back to 600 picoseconds in time. Time is going this way, and it only goes that way so far in our understanding of physics so far, that we can't make it go backwards. So we can't do this. So we're stuck with this thing here, and we're going to have to use another type of magic trick to get rid of that. And so what we're going to have to ask is we're going to have to ask the compiler to help us out. And we're going to ask the compiler to look at the code that we wrote, which does a load and then immediately uses the load, just as you might expect. And we're gonna ask the compiler to do the following. We're going to say, hey, very often, we're going to go and get several items out of a data structure. Very often, if we go to the bank and the data structure that represents your bank account, we'll get both of the, your checking balance, your savings balance, and your biweekly salary, we'll get all those things because we need them all. So we're going to ask the compiler to notice that, to look at a little bit bigger section of code, to notice that we're going to get several different values, and to go ahead and group getting those values together. And by doing that, we're going to put in something that doesn't have to wait into that cycle where we had to wait before. So before, on the previous slide, we saw that we had to insert a stall here, right? So that's where the bubble appeared between the load and the use of the load because of this. And so we're gonna ask it, oh, go down here and see, here's another load that's also basically, getting something out of that same data structure. And we're going to ask the compiler to move it up here. So move it from here to here. And that's called promoting it. So we're going to promote the second load. And when we promote the second load, we will fill that stall slot that would have gone in here. And not only that, the stall slot that would have gone in here because we did this load and then did its use of load also disappears because we've moved this load way early. And so this guy can get done immediately. And so both this add and this add are no longer now in the shadow of their load. They're no longer in the cycle immediately after their load because this guy is waiting on this load, and oops, go away. This guy is waiting on this load, and he's now got this guy in between, and this guy is waiting on this load, so he's got plenty of stuff in between. So anyway, so this thing went from 13 if you count total completion, but we don't care about that. We can just count at 1, 2, 3, 4, 5, 6, 7. It went from 7 plus 2 because the 2 stall cycles that had to get inserted. So it went from 9 to 1, 2, 3, 4, 5, 6, 7. Oops, 7. So it went from 9 cycles to 7 cycles. And more importantly, it kept the pipeline at maximum efficiency. So once we rearrange the code this way, we will get our pipelines continuing to run at fully overlapped rate. So the full 5x, our full 5x benefit is still intact if we can get the compiler to just help us out a little bit. And so this was one of the, again, the realizations and revolutions of the RISC revolution that happened back in the 80s, that people said that, hey, we can write compilers that are this smart. Once we have enough registers, if you give us enough registers, and if we use these nice graph coloring algorithms, we can do this. This is a thing that the compiler can do, and it can make our computers faster because we can build them as simple as possible, and the compiler can help us, fix any minor problems like this, like these 2 stall cycles. And so we rely on the compiler to do this for us. And it can do it almost all the time. Very seldom are loads done one. Very seldom will you just find one load in a program. They're almost all together. Okay, so we'll break again for just a minute, and we'll come back and do the hardest of the problems, which is the control hazards. All right, so our our final hazard type here is the control hazards. And as we know, the branches the branches, whoops, come on, pen, work. The branches determine the control within our processor. They determine, when we get to the end of a loop, whether we go back to the loop or go on. They are the things that we use to build the if then else constructs. So branches, make the flow of our program change. So simply put, that, when we go and fetch the next instruction, it depends on what the branch did. Now, the branch, of course, you fetch the instruction, and as usual with any instruction, it takes a while for it to do its thing. So it takes a while for us to know whether the result of the branch is going to go or not. And so in our RISC architectures, we're going to compare these registers, and we'll also do the calculation of where to go as soon as we can. As soon as we fetch that offset out of the instruction, we'll do that addition to the program counter, and we'll basically compare the registers at the same time. And as soon as we get this done, then we'll use that to change the flow of instructions. And let's see in a picture here how that works. So we'll go and draw our own picture, because we'll want to annotate it. And so what we want to do is we're just going to do something that we'll do often. We'll just draw a sequence of instructions, which we can just represent as, these groups of 5 pipeline stages, all overlapped. So we have instruction fetch, instruction decode, execute, memory, and write back. And then the next one starts, instruction fetch, and then the next one starts, instruction fetch, next one starts, just like our laundry, just like overlapping, doing the laundry. Now, the best case is that, if this is the branch instruction, is that at the output of the execution stage, that's where we do we compute that signal that he calls 0, which meant the operands were equal. Operands were equal. The result was 0. The result of the subtract was 0. Result of subtraction was 0. 0 is that 0. Okay, so we have that here, and recall that the way we fetch the instruction is that we have a thing here called the program counter, and during this cycle, the program counter accesses the instruction memory. That's what instruction fetch means. It means our program counter addresses and fetches out an instruction, which again we then take and we decode it in the next cycle, and so on. And so what we need to do is we've got that mux that's choosing between program counter plus 4 and program counter plus 4 plus the branch offset. And that feeds into the program counter. So we're going to want to take this result here from the execute stage, this subtraction, and we're going to feed that result down and try to pick the right input to that program counter. And basically that means control this mux. And this mux is, physically sitting right before the program counter. I drew it back here, but it's not back here in time. It's just, we just put it there to show that, just so we could see it. But that mux is there, and we just need to switch it, just before the rising edge of this clock. Each one of these cycles, right, represents a clock and so on. So right before the rising edge of this clock, we need to switch this mux so that we get the right value transferred to the output to fetch the instruction, the next instruction. And so this path as drawn might be very tight. We'll look at a diagram a little bit later where we say that, well, we don't actually manage to get that done until here. But for right now, let's assume we get it done here and that we come down here and switch this mux. You can see that if we take the branch, and here's the key point, if we take the branch, that this instruction and this instruction will have to get thrown away because we didn't have the branch plus offset value, the target of the branch. We don't have the target of that branch fetching a new instruction until here. So the instruction that we fetched here and here, these were just, this was PC, this was PC plus 4, and this was PC plus 8. It was the current instruction and then the next two instructions, because there's nothing else we can fetch until we make that branch decision. We just continue to fetch straight. So this is, of course, again, a huge problem because we have two, and as we said, possibly three, depending on when you decide that you can make this decision and get here and switch this multiplexer in time. So it's possible that you're going to throw away 2 and maybe 3 instructions if you take the branch. And of course, if you didn't take the branch, that's fine. You'll just go through and you'll continue executing, PC plus 4, PC plus. So this one here was PC plus 12 because it's just one more than this one. And this is PC plus 12 plus offset now that we've drawn it all out. Okay, so we'll just, acknowledge right here that this is a big problem, these two instructions. And why is it a big problem? Well, what do we know? We know that ALU type instructions are about, about 50%. And we know that load stores are about 50% of 25% of the instructions. And we know that branches are about 25% of the instructions. So let's think about what that means, of course. That means that on average, every 4th instruction is a branch. And so if every 4th instruction is a branch and every time we have a taken branch, we insert, these 2 instructions that don't do anything. Basically, we have to turn these into no-ops because they're doing the wrong thing, but they're on the wrong path, the wrong execution path. Since we have to throw those away, that has a big impact on our performance. And so we'll need to solve this problem somehow. There, that's not where we want to be. Right. So today in modern hardware, modern processors, we're going to do branch prediction. Now, it's very worthwhile noting that branch prediction is, one of the more recent things that has been added to processors, because when the first RISC processors were designed, so when the MIPS architecture first came out, it had, no branch prediction. And the reason it had no branch prediction is because we're going to find out the branch prediction takes a lot of transistors to do it in a reasonable way. And so since it takes a lot of transistors, and when the RISC architectures came out, we were, much closer to the beginning of Moore's law. We didn't have enough transistors to do branch prediction. And so branch prediction is, is if you will, a second generation thing for improving the speed of our processors, but it's very, very important. And as the pipelines became, and when we say longer here, we can just change longer to be more complex. And more complex, we'll end up seeing later means, to do multiple instructions per cycle. And we'll get to that next week. But we want to try and do more than one instruction per cycle in the highest performance processors. And the more complex, the more instructions you do per cycle, the more of them that you're going to have to throw away if you waiting on the result of the branch. And so, as it says here, the penalty for waiting on the branch result to be resolved becomes too long. So instead, we're gonna, once we see a branch for the first time, from then on, we're going to predict what the outcome of that branch will be. And there's a whole science. Many PhDs wrote their theses on how to do, the best branch prediction. The best branch prediction. This is a problem that's been worked on for years and years now. And people continue to keep working on it because people continue to have, because of Moore's law, up until recently, you had a lot of free transistors coming to you. And so with all those additional transistors, you could do better and better job of branch prediction. And branch prediction is very important to the performance, not only because of those cycles that you're able to not throw away, but also branch prediction is it's the underpinning of doing what we'll later talk about is speculative execution. And speculative execution means that we're going to not only predict branches, we're going to predict multiple levels of branches. So we're going to predict a branch, and then we're going to start executing the instructions based on having predicted that branch. And we'll come to another branch 3 cycles later, and we'll predict that one, and we'll then start executing the instructions after that branch. And we'll keep doing that as long as we have hardware to do it. And so the accuracy then, of branch prediction is very important. Not so important if you have a simple processor that just predicts the current one and then executes based on that. But as soon as you do these very complicated machines, which we'll find out are called out of order machines, where we, go and look for instructions to execute independent of where they are. As soon as we have a machine like that, the branch prediction becomes absolutely critical that the accuracy be, extremely high. And when we say extremely high, we mean, 95% plus accuracy. And so that's the state of the art of branch prediction today. Every processor out there these days virtually, have some branch prediction in them, some pretty sophisticated branch prediction. And the highest performance machines have incredibly sophisticated branch prediction. So, and here's what they have. The first, the first branch predictors that came out, they looked at just what kind of code you were in. Were you in a loop, or were you in an if then else? And it would just make prediction for a loop. You would predict taken. And for an if then else, well, really, quite frankly, you couldn't predict them very well. I mean, you could predict not taken, you could predict the then instead of the else, but depending on how that piece of code was written, that it may have been more like 50-50. And so, that's therefore not very good branch prediction. So anyway, but in the, we're not doing that anymore. In the real world, we're doing, what's called dynamic branch prediction. So we have hardware that measures what the branches have done in the past. So they record history of each branch. And they record the history these days in a very sophisticated way. So it's not just, when it says recent history here, it's multiple threads of recent history. Multiple threads of recent history. That means it's, recent history, but coming from different places. So different ways of getting to that same branch. The history is adjusted based on where you came from. So very, very sophisticated technology today for branch prediction. And it's still, when you're wrong, you end up flushing 3 or 4, however many instructions it takes. But these days you're not wrong very often. And so we get, a much higher performance. So the big picture for pipelining then is that we're going to increase the throughput dramatically. So for a simple, machine, we get this 5x with a 5-stage pipeline. And if you imagine, a modern machine that issues 2 instructions per cycle, then, you're going from, 5x to 10x, because you're getting 5x from the pipelining and 2x from the fact that you're issuing 2 instructions at a time. So we're increasing the performance dramatically by parallelism, right? Both those are cases of parallelism. 5x times, 2x. And then to make this all work and go smoothly, though, we have to do these, we have to supply magic potions to fix these basic problems. We either have to supply more stuff, smarter stuff, all comes down to more transistors. So Moore's law equals more transistors equals more cleverness equals more performance. And the instruction set had to be designed from the start to make this all work really well. Again, as we noted, that the x86 architecture, the CISC architecture, what we've said and what we've learned as we've gone along is that the way they make their architecture work these days is that they put the CISC through a conversion in hardware. So they use Moore's law to convert it to RISC. And then they put RISC through everything, they just do the same thing, everything we've talked about in this whole course. They just have to spend a few million transistors right in the very front to convert their CISC instruction set to a RISC instruction set. And then they do the same thing everyone else does, including very sophisticated branch prediction and all the things we just mentioned. So when we come back next time, then we'll put in the pipeline registers. And then once we put in the pipeline registers, we can start putting in the hardware to do the magic tricks. And so we'll do that, as soon as we come back. Okay, so the last thing we want to look at for tonight's lecture is this putting the registers into our actual pipeline so that it can actually, separate out and run in a pipeline fashion. We already conceptually can see how that happens, but we're just gonna put in the pipeline registers now and see exactly where they go and see what things are held in each stage, and just look down at one more level of details. And we're gonna look at the load and store instructions as an example of this level of detail. So you see what we've done is we've taken those same places where we had the dash lines, and it's again, remember the same picture we've always had, the same basic blocks. And now we stick in those things that we learned about called registers that work by transmitting what's on their input to what's on their output at every rising clock edge. So at every rising clock edge, in every one of these cycles, what's here is going to go to here, what's here is going to go to here, what's here is going to go to here, and so on. And so they're just illustrating it here for the first pipe stage, and they're saying, okay, so during the instruction fetch, what we have is the program counter feeding its address into the instruction memory, and the instruction memory having its value sitting at the input to the first stage pipeline register. And you'll see that they call it the IFID. So it's the instruction fetch, instruction decode register. It's the register that sits at the boundary of those two stages. And you'll see that the other registers are named similarly. And so when the rising clock edge happens here, the instruction will go from having just been read out of the memory. It'll move to the output of the register, and now it'll be there available for the whole next cycle. So that's what happens during the instruction fetch cycle. And we have a pipeline register there to capture the result. So we want to capture the instruction read, the instruction fetch. Okay. And then we just go on from there and we just do the same thing, right? So now we're doing an instruction fetch for the next instruction. But during this cycle, we're doing the instruction decode for the instruction fetch that we just did. As we said, we moved what was there to here. And now during this time, we're reading the register ports, reading the register file based on those 5-bit register values that are in the instruction. And then we take the whole cycle to do that. And at the end, we're ready to put those outputs, to put the actual value that's in the register file, to move them to the output of this register on this rising edge. And then we're ready to do the next stage. And now you just see that happen. So this just clicks through one stage at a time. This is the instruction going through. So if we're doing a load, we looked in detail at what happens on a load. We take the register value from here, the base address of the data structure, and we add the offset into the data structure. And then we, transmit it to the next cycle. And if we're doing a load, then that address indeed goes to the data memory just as it's shown, and we see that happening in the next cycle. And so in the next cycle, we read the data memory based on the address that we just computed in the previous cycle. And then we register it at the end of its cycle, the rising edge there. And then we're going to send it back to be written into the register file. And here's that happening. So here's the write back stage. So write back stage, WB stage of this load instruction, takes the result, writes it back in to the register file. All right, now we want to pay very close attention for just 1 minute, because the adjustment we're about to make here is quite fundamental. And once we make this adjustment, we're going to use the adjustment that we made for a bunch of things. And there's so we'll see what that means. So what it says here is that we have the wrong register number. What does that mean? So it means that when we're in the write back stage of the load instruction, and we've got the data coming back here that we want to write into the register file, that at that time, the value that's stored here is the value for the instruction decode, not of the load instruction. The value of the instruction decode of the load instruction disappeared a long time ago. The load instruction is now here in this cycle. So we now have the instruction that's 1, 2, 3 instructions after, 3 instructions later than the load. So wherever the load was, there's 1, 2, 3 more instructions, and that this instruction here is what's currently sitting there. And so what that means is that the 5-bit value that's coming out of here, that's in the RD register. So there's a RD register here, we know. And the value that's pointing into the place in the register file that says where to write is clearly the wrong value. It's the value for this instruction. We need that value for this instruction, the load word that's sitting here. So how are we going to fix that? So this next picture is quite fundamental. So pay very, very close attention here, because we're going to, once we fix this again, we're then going to use this fix for a lot of things. So note that what we do is that at the same time that the LW is here, and that's when the RD is valid. So if we go back to the picture where we were doing the LW instruction decode, we're doing that, we're pretending we're doing that right now. We're going to take the RD field and we're going to dump it into, this is 5 bits, and this is coming out as 5 bits. So we're going to dump it into an additional 5 bits of register that we're going to tag on here to this big register that's, you know, one of our pipeline registers. These are our pipeline registers. And then we're just going to keep sending it along, so that at the same time that we have the data here, that we have the correct RD for that data. So as that instruction moved through the pipeline, we just kept track of that 5-bit field, that 5-bit RD field, so that when this goes back to here, that 5-bit field goes back to here, so that we have the right address to go with that data, so that we have the right place to write it. So that's key, that we had to keep that value. We have to keep that value until we need it. That 5-bit RD field has to be staged along with the instruction until we actually need it, so that we can point to the right place to write the data that we loaded from the memory. So think about that carefully. Make sure that in your head you've got why that's true, and this very simple fix of how to make it happen is you just have to stage it along, just along with everything else that instruction is doing. And for the store, of course, there's no write back. And so once we get to here where we compute the address, we go to the next cycle where we store the value, right? So we read the value from here, computed the address here. So here's the address computation. Here's the data. So it all moves to here when this clock edge happens. And now we write it into the memory. And during the write back stage, therefore, we do, as you can see, nothing. Nothing happens in the write back stage of a store. So a store is done. It's done after it finishes this. Nothing happens in the write back stage. All right, so here's, you know, an entire set of instructions all put together. And when we come back next time, next lecture, we'll pick up from this point and show, you know, how all of these pipeline stages now all work together, and how to make bypassing and all the hazards and fix all that stuff. So we'll do that when we come back. So we have a quiz for this lecture. Let's see, let me find it real quick. 21st. Three, 3, 7, 1, 2. Whoops, 3, 3, 7, 1, 2. For the in-class quiz for tonight. And so with that, I will stop the recording and we'll pick this up live on Tuesday.